Good morning everyone. Today we will discuss about ultraviolet UV spectroscopy. Introduction. One of the important field of activities of an organic chemist is the determination of a structural formula of various substances. In the earlier days, the structure elucidation was mainly based upon the study of a classical physical properties, melting point, boiling point, refractive index, etc., and the chemical reaction of a compound. The procedure include was rather laborious and time consuming. However, in the last 50 years or so, some remarkable physical method has been developed to serve as a powerful tool for structural analysis. On these, the most useful and commonly employed method are the spectroscopy method, which are based upon the interaction of electromagnetic radiation with the substance under examination. These methods may be further involved the study of ultraviolet, UV, infrared, IR, nuclear magnetic resource resonance NMR, and mass spectra. Mass spectroscopy is employed to determine the molecular mass and molecular formula of the substance, while UV and IR are used to determine the nature of functional groups. Finally, the NRM spectroscopy is used to know the complete structure, including the stereochemistry of a substance. The major advantage of employing this spectroscopy method for structural determination and identification of a substance are as follows. First, they need very little time, and the information obtained is often a permanent record in the form of a chart. Second, the substance is required in very small quantities of the order of 1 mg. Third, methods are extremely sensitive and highly reliable in stabilizing the structure of a compound and analysis of a mixture of closely related compound. Fourth, they can be used for the detection and identification of even very short-lived reaction intermediate. Fifth, during the spectroscopy study, except mass spectroscopic, the compound is not generally affected chemically and can therefore be recorded unchanged. Sixth, continuous analysis is often possible, facilitating the study of a reaction rate, etc. In this chapter, we shall deal with the basic aspects of ultraviolet spectroscopy, the electromagnetic spectrum and spectroscopic studies. Electromagnetic radiation. Many spectroscopic techniques are based upon the interaction of a compound with light or some other form of electromagnetic radiation. It is well known that light and other electromagnetic radiation are different from of a form of energies which has a dual nature. They have the properties of both wave and particle. They are called electromagnetic radiation because they consist of oscillating electric field and magnetic field which are perpendicular to each other and perpendicular to the direction of the interaction of a radiation. Some important characteristics of these radiation are: first, the energy of these radiation is inversely proportional to the wavelength or directly proportional to the frequency. Second, these radiation do not require any physical medium and can be transmitted through empty space. For example, light reaches us from the sun through empty space. Third, all type of electromagnetic radiation travel through space with the same velocity, which is nearly 3 into 10 to the power 8 meter per second. Electromagnetic radiation can be described in terms of their characteristics such as the wavelength and frequency. First, wavelength, it is a distance between two adjacent crusts or a trough in a particular wave. It denoted by the symbol lambda. The wavelength is usually expressed in meter, micrometer, nanometer, angstrom. 1 micrometer is equal to 10 raised to power minus 6 meter. 1 nanometer is equal to 10 raised to power minus 9 meter. 1 angstrom is equal to 10 raised to power minus 10 meter. An older term of micrometer is micron, and an older term of a nanometer is known as millimicron. Second, frequency. It is the number of a wave which pass across a point in 1 second. It is denoted by the symbol V, read as normal. The frequency is generally expressed in cycles per second, CPS, or simply second inverse or hertz. 1 hertz is equal to 1 CPS, cycle per second. The frequency and wavelength are related to each other as nu is equal to c by lambda, where c is the constant velocity of light. Third, wave number. It is the reciprocal of wavelength and represents the number of waves per centimeter. It is denoted by the symbol nu bar. Wave number is generally expressed in centimeter inverse, reciprocal of centimeter. Wave number is related to wavelength and frequency as nu bar is equal to 1 by lambda is equal to nu by c, where c is the velocity of radiation in centimeters, such that 3 into 10 to the power 8 centimeter per second. 10 centimeter per second. In SI system, the wave of a unit of a wave function is a meter inverse. Fourth, energy of electromagnetic radiation. Electromagnetic radiation are associated with discrete energy unit called quanta or photons. The energy of a photon is directly proportional to its frequency or inversely proportional to its wavelength, as shown by the following equation. E is equal to h nu is equal to c by lambda, where h is the Planck constant, 6.625 into 10 to the power minus 34 joule. Second, electromagnetic spectrum. Visible light which can be detected by human eye constitute only a few very small particles. Electromagnetic radiation. The full range of these radiation is indeed very large, and their wavelength vary from a small fraction of a meter to a many kilometers. The arrangement of entire range of electromagnetic radiation in increasing order of their wavelength or decreasing order of their frequency, known as electromagnetic spectrum. The complete electromagnetic spectrum, along with common names used to identify different ranges of wavelength, is shown in figure 4.1. Of the complete electromagnetic spectrum, spectroscopy techniques are concreted primarily with radioactive frequency radiation (NMR), infrared radiation (IR), and ultraviolet visible radiation (UV). Principle of absorption spectroscopy. It is interesting to note that practically all the important spectroscopic methods used for structural analysis belong to the field of absorption spectroscopy, which studies the absorption of electromagnetic in a relationship to molecular structure. When a beam of electromagnetic radiation is passed through a substance, the radiation may be either absorbed or transmitted depending upon the wavelength of the radiation and the molecular structure of the substance. Absorption of radiation would naturally be about the increase in energy of a molecule, the energy gained by directly proportional of a frequency or inversely proportional to the wavelength of a radiation. The increase in energy of a molecule leads to electronic excitation, whereby electrons are raised to higher energy level. Alternatively, it may be being about an increase only in the vibrational or rotational energy of a molecule. Electronic excitation can be caused by only high energy radiation such as ultraviolet and visible radiation. On the other hand, vibrational or rotational energy level can be raised even by relatively low energy infrared radiation. A very important condition for a molecule to absorb electromagnetic radiation is that the energy of a photon of the radiation must be equal to the energy difference between two vibrational or a rotational or electronic energy state of a molecule. In other words, the particular wavelength of a radiation that a given molecule can observe is determined by change in vibrational or rotational or electronic states that are permitted to a molecule of that structure. The absorption of radiation is observed instrumentally by passed radiation through a sample of a substance and automatic analysis of intensity of a transmitted radiation. A record of amount of radiation absorbed or transmitted by a given sample of a function of a wavelength of a radiation is called absorption spectrum. One might accept an absorption spectrum to consist of a series of a line, but actually the spectrum is made of absorption band with peak of a maximum intensity. The instrument used for recording a spectrum is known as spectrophotometer or spectrometer. Having discussed the principle of spectroscopy, we proceed further to discuss ultraviolet spectroscopy in some details. Ultraviolet spectroscopy. Ultraviolet spectroscopy includes the measurement of absorption of light in visible and ultraviolet region. Visible region 400 to 800 nanometer, UV region 200 to 400 nanometer. By the substance under investigation, since the absorption of light involves the transition from one electron energy level to another within a molecule. UV spectroscopy is also known as electronic spectroscopy. It will be quite appropriate at the stage to study the law which govern the absorption of light. The absorption law. There are two laws which express respectively the relationship between absorption of light by a substance and its molar concentration and the length of a path through which the light passes. These are Beer law. According to this law, when a beam of a monochromatic light is passed through a substance dispersed in a non-absorbing solvent, the absorption of light is directly proportional to molecular concentration of the absorbing substance. Second, Lambert law. This law states that when a beam of monochromatic light is passed through substance, the absorption of light is directly proportional to the path light of the sample of the substance. Third, Beer-Lambert law. The two laws stated above can be combined to get a general absorption law, termed as Beer-Lambert law. It may be stated as the absorption of light by a substance at the particular wavelength is proportional to the number of molecules of the substance in the path of a light. Mathematically expression given below, Beer-Lambert law may be expressed as I naught intensity of incident light, I intensity of transmitted light, C concentration of the absorbing substance in mole per liter, L path length or thickness in centimeter of a cell containing the sample, nu proportionality constant known as molar absorptivity, sometimes referred as a molar extinction coefficient or simple extinction coefficient. The expression log I naught by I is termed optically density or absorbance. It is a measure of absorbance of radiation by a sample. Therefore, Beer-Lambert law may be expressed mathematically as A is equal to log I naught by I is equal to ECL. Limitation of Beer-Lambert law. Beer-Lambert law is strictly obeyed when deal with the UV spectroscopy of a single species. However, if a sample contains different structural forms of a molecule in equilibrium with each other, such as in case of a keto-enol tautomerism, the law is not obeyed. It is also not applicable if the solute sample and solvent interact with each other to form complexes. Fourth, molar absorbability. Epsilon. It is a proportionality constant which related the observed absorbance A and a particular wavelength lambda to the molecular concentration of absorbing substance and length L of the path light in a centimeter. It may be expressed as epsilon is equal to log I naught by I divided by CL. A by CL. Molar absorbability Absorptivity is a measure of intensity of absorption at a particular wavelength, and the dimension of centimeter square mole per inverse. Centimeter square mole per mole. But these units are seldom used. It is a characteristic property of a compound and is not affected by the concentration of the length of the path of a light. Its value range from 0 to 10 to the power 6. Value above 10 to the power 4 constituent high intensity absorption, while value below 10 to the power 4 are low intensity absorption. Light first and transmittance of a sample will be naturally given by relation T is equal to I naught by I. Transmittance 100 into I by I naught. Mechanics of recording the UV spectrum. Presentation of a spectrum. Excellent UV spectroscopy are now available, which are conveniently recorded the spectra over the range of 200 to 800 nanometers. Since oxygen of atmosphere strongly absorbs light at about 200 nanometer and below, the use of wavelengths shorter than 200 nanometer is not practicable unless special vacuum techniques are employed. The ultraviolet spectra are always recorded on a wavelength scale in millimicron or nanometer. Procedure. For recording the ultraviolet spectrum, the given compound is generally dissolved in some suitable solvent which does not itself absorb light in a region under examination. The commonly employed solvents are 95% ethanol, hexane, and water. The solution of a compound is placed in a suitable transparent container which does not absorb light in the region being studied. Generally, a quartz cell of 1 centimeter path length is used for the purpose. Glass cannot be used since its absorption strongly in UV ultraviolet region. At the same time, some solvent is taken separately in another quartz cell which serve as reference cell. The sample solution and the solvent are exposed to ultraviolet and visible radiation in a spectrophotometer, in which a hydrogen discharge lamp is usually employed as the source of a light of the ultraviolet region 200 to 400 nanometer, while a tungsten filament lamp is used for the visible region 400 to 800 nanometer of radiation. The spectrometer operates by comparing the amount of light in the beams transmitted through the sample which the refer beam which passes through the reference cell. The compensate for the absorption of light by the cell and the solvent. In this way, the spectroscopy means the amount of light absorbed by the compound at each wavelength of the ultraviolet and visible region. This absorption gets recorded on a chart part as a plot of a wavelength and of the entire region on the horizontal axis. Various the absorption of light at each wavelength. The spectrum obtained consists of a small number of broad peaks. Quite often, only one peak is seen. UV spectroscopy. A simplest diagram of UV visible spectroscopy is shown in figure 4.1. It consists of the following part: a source of radiation which emit all wavelengths of UV radiation. The commonly used source of light in UV region is the hydrogen and deuterium discharge lamp, while a tungsten filament lamp is used for producing visible light. Second, monochromator, which separates the radiation into individual wavelengths. The single wavelength of a radiation is split into two beams, one of which pass through the sample cell, which the other passes through the cell reference cell. A detector which continuously measures the intensity radiation of a beam transmitted through the sample and the solvent respectively. A recorder chart paper which automatically records the absorption of light at which wavelength as a graph of absorption versus wavelength. Presentation of a spectrum. The UV spectrum of 1,3-butadiene in hexene is shown in figure 4.3. It may be seen that absorption of a UV radiation absorption is maximum at 217 nanometer top to peak. The spectrum is absorbed as a single absorption peak using the notation lambda max is equal to 217 nanometer. In reported the UV spectrum of analytical purpose, the molar absorptivity epsilon, which indicates the intensity of absorption at the wavelength of maximum absorption, is also quoted along with the lambda max. For example, the molar absorptivity of a 1,3-butadiene at lambda max is equal to 217 is 20,900. Therefore, the UV spectrum is reported as 1,3-A-butadiene. Lambda max is equal to 217 nanometer. Sometimes the ultraviolet absorption curve are also present by plotting molar absorptivity wavelength is shown below in figure 4.3a. It may be seen that the maximum molar absorptivity about 15 at lambda max is equal to 279 nanometer. Since the UV spectra generally show broad peak and valley, the actual spectra are rarely used. The spectral information is given by listening the wave and waves of lambda max along with the molar absorptivity for each value of lambda max. Principle of UV spectroscopy. Absorption of visible and ultraviolet light reduce change in the electronic state of a molecule associated with excitation of an electron from a lower to higher energy level. But in this case, we noted that each electronic level in a molecule can be noted that in a molecule associated with a number of vibration sublevel with small energy separation and some irrational level in turn as association with a number irrational sublevel with still some smaller energy. Therefore, in its transition to higher energy level, an electron can go from any of the level corresponding to various vibrational and dash states in the ground state to any of the level in the excitation state. Appears a broad band and not sharp in the spectrum if the electronic excitation of the molecule has occurred without any accompanying change in a vibrational and rotational subcells. The spectrum would have the assistance of a sharp line as in the case of absorption spectrum of atom, with each line representing a electronic state, but due to mixing of a vibrational and rotational change with electronic change in the molecule, there will be a large number of possible transitions required, only slightly different energies. This will require the absorption of a large number of wavelengths which are very close to each other. As the result of absorption, spectrum contain a large number of lines which are too close together to a distinguish separation and are recorded in form of a broad band. The spectrum obtained, as stated earlier, the spectrum is described in terms of a position of the top of a humps and the molar absorptivity. Electronic excitation. Electronic transition involve the promotion of an electron from one orbital to another orbital, higher energy in a molecule. The electron promotion may be first sigma electron, such that an electron present in a sigma molecular orbital. Second, pi electrons, such that an electron present in pi molecular orbital. Or third, an electron present in non-bonding orbital and illuminated with the heat of a electron pair in a formaldehyde as shown in the right hand side. The higher energy orbital are anti-bonding molecular orbital which may be vacant in the group state of a molecule. Anti-bonding orbital associated with the sigma bond is called sigma star. A sigma star orbital, and the associated with the pi bond is called pi star orbital. Since the n electrons are not concentrated in a bond formation, they are non-bonding orbital associated with them. The electron transition takes place in a ultraviolet and visible region are of the following type: sigma to sigma star, n to sigma star, n to pi star, and pi to pi star. Figure 4.5 give a general idea of relative amount of energy required for a various type electronic excitation. A brief account of a various type of electronic transition is as follows. First, sigma to sigma star transition. Transition in which a sigma bonding electron is excited to an anti-bonding sigma star orbital are called sigma to sigma star transition. This transition can be shown only by compounds such as saturated hydrocarbon in which all valence shell electrons are involved in the formation of sigma bond. The energy required for the formation of transition is very high, and consequently these occur at a very short wavelength. For example, in methane, the absorption of energy for the transition occur at only 1 to 5 nanometer. Since these wavelengths are lesser than 200 nanometer and fall in the vacuum UV region, the usual spectroscopy technique cannot be used in case of a transition. Second, N2 sigma star transition. These are electronic excitation from a non-bonding atomic orbital to an anti-bonding sigma star orbital. Compound having non-bonding electron and heteroatoms such as oxygen, nitrogen, sulfur, and halogen can show N2 sigma star transition. These transitions are a low energy and hence occur at a low wavelength than sigma to sigma star transition. For example, N to sigma star transition in methyl chloride require absorption of energy at 174 nanometer. The energy required for the transition decrease with the decrease in electronegativity of the heteroatom, and therefore the wavelength of absorption increase. For example, methyl chloride absorbed at 174 nanometer while the methyl iodine absorption take place at 258 nanometer. Similarly, amines absorb at a higher wavelength than alcohols, as nitrogen has a lesser electronegativity than oxygen. These observations can be attributed to the fact that greater the electronegativity of heteroatoms, more firmly the non-bonding electrons are held by it, and therefore more energy is required for N to sigma star transition. Hydrogen bonding of a compound with the solvent also shifted the absorption to a shortened wavelength. But in generally, N to sigma star transition are not of much importance. Third, N to pi star transition. These are the transition in which an electron in a non-bonding atomic orbital is promoted to an anti-bonding pi star orbital compound having double bond between heteroatoms such that C double bond O, C double bond S, and N double bond O. Show this transition which appear a weak absorption band. This transition require only a small amount of energy and take place within the range of an ordinary ultraviolet spectrophotometer. However, the intensity of absorption is generally very low. For example, the carbonyl group of saturated aldehyde or ketone exhibits an absorption of a low intensity at about 285 nanometer. Fourth, pi to pi star transition. The transition in which a pi star electron is excited to an antibonding pi star orbital are called pi to pi star transition. These has relatively high energy required than n to pi star transition, and absorption generally take place outside the ordinary ultraviolet region for simple molecule containing isolated unsaturated centers. But the intensity of absorption is very high. For example, the pi to pi star transition for a simple aldehyde and ketone produce an absorption band of high intensity at about 180 nanometer. For a simple alkenes like effect of conjugation. Conjugation of a double bond lower the energy required for the electronic transition. As a result, molecules containing conjugation systems such as carbon double bond carbon to single bond carbon double bond carbon and C double bond C single bond C double bond O absorption the radiation of long wavelength than in case of a non-conjugating system, and absorption band appear in the ordinary ultraviolet range. For intense 1,3 butadiene in such shows lambda max 217 nanometer in a contrast to ethylene which show lambda max 175 nanometer. To understand the effect of a conjugation on a lambda max, let us start with ethylene, which is the simplest in conjugation alkenes. The double bond in ethylene consists of a sigma bond formation of a combination of sp2 hybridized orbital of a 2 carbon atom, and in pi bond formation of combination of unhybridized 2p orbital. Due to large difference in the energy of a pi bond and the pi antibonding molecule orbital, pi to pi star transition take place with absorption of radiation below 200 nanometer. Therefore, these transitions occur only in a far ultraviolet region. In a conjugation system such as 1,3-butadiene, these are two ethylene unit in conjugation with each other. Due to the conjugation, the pi bonding orbital of two ethylene unit interact with each other to form two new bonding orbital pi 1 and pi 2 of different energies. Similarly, this is the formation of two orbitals pi 3 star and pi 4 star of different energy for a two ethylene unit. The energy difference between higher or occupied pi orbital and the lower unoccupied molecular orbital for 1,3-butadiene is less than it is for ethylene, as the molecular pi molecular orbital and lower molecular orbital energies gap becomes smaller. The position of energy absorption move to longer wavelength, which falls within the ordinary ultraviolet region. With the increase in the number of double bonds in conjugation, the energy difference between higher pi bond molecular orbital and lower pi bond molecular orbitals further decrease. So that absorption moves to still lower wavelength. The spectrum of 1357 octatetranes in hexa exhibits lambda max 290 nanometer. If these are enough double bond in conjugation, absorption will ultimately move into the visible region and the compound will be colored. For example, beta cardones, a natural occurring yellow pigment containing 11 double bonds in a conjugation, owns its color absorption in the visible part of light, lambda max 455 nanometer. Another effect of a conjugation is that with the increase in conjugation, the number of possible UVL transition increase and the spectrum become more complex. To sum up the above discussion on electronic transition, it may be stated that the organic chemistry is primarily interested in two types of transition, particularly in conjugation. These are pi n to pi star and pi to pi star. It may be noted that transition of antibonding pi star orbital are associated with only unsaturated centers of a molecule. Transition possibilities. It is interesting to note that it is not necessary that explore of a compound to ultraviolet visible light must always lead to electronic transition. On other hand, the possibility of particular electronic transition. First, allowed transition or forbidden transition. Allowed transition. This transition which has maximum energy 10 raised to power 4 or more, and possibility of these occurrence is very high. These are generally due to pi to pi star transition. For example, pi to pi star transition of 1,3-butadiene in which show absorption at 217 nanometer has maximum energy 20900 represent an allowed transition. The pi and pi star orbital included the transition lie in the same plane and undergoes overlapping to a large extent in the exciting state. Therefore, pi and pi star transition are highly probable. Second, forbidden transition. These are transitions for which maximum energy is generally less than 10 raised to power 4. These are usually related to n to pi star transition. For example, n to pi star transition of a saturated aldehyde or ketone showing weak absorption near 290 nanometer and having maximum energy less than 100 is a forbidden transition. It, show, it should be clearly understood that forbidden transition does not mean that such a transition cannot take place at all. It just tells us the possibility of transition is very low. To clarify this statement, let us consider the n pi star transition. The orbital containing the n orbital electron present on heteroatom lie in a plane perpendicular to the plane of a pi star molecular orbital. The reason in the space belong to these orbitals can overlap only to a very small extent. As a result, the probability of excitation of an electron to pi star orbital is very low. Concept of a chromophores and oxochromes. Chromophores. This term chromophores was originally used to denote the functional group or some other functional group features, the presence of which impact a color to a compound. For example, nitro compound is the chloropores since its presence in a compound impact color yellow color to compound. But these days, the term chromophores is used in a much broader sense. It is not defined as any group which exhibits absorption of electromagnetic radiation in visible or ultraviolet region. It may or may not impact any color to a compound. Table 4.1 lists some sample chromophores group along with their lambda max and E max and the type of a transition involved. It may be seen that chromophores are two types. Chromophores such as C double bond C and C triple bond C, which contain pi electron and undergoes pi to pi star transition. Third, chromophores such as C double bond O and double bond N NO2, which contain pi and n electrons. They can undergo pi to pi star transition as well as n to pi star transition. Two compounds having the same chromophoric group generally exhibits absorption at nearly the same wavelength and having nearly the same molecular absorptivity. Therefore, it should be possible to identify the presence of a particular functional group in an unknown compound by the comparing of its UV spectrum with the data of already known compound, but the position of absorption maximum and the intensity of absorption can be modified by a number of factors discussed below in section 1.93. Oxochrome. An oxochrome is a group which itself does not act as a chromophore, but when attached to a chromophore, it shifted the absorption maximum toward long wavelength along with an increase in intensity of absorption. Some commonly known as oxochromes groups are OH, NH2, OR, NHR, NR2. All oxochrome containing one or more non-bonding pair of electrons. When an oxochrome attached to a chromophore, it leads to conjugation or helps in extending conjugation by searching of its non-bonding pair of electrons as shown below. Due to conjugation, there is a decrease in energy difference between the group state and excited state of a group. As a result, the absorption shift of long wavelength at the same time, there is an increase in intensity of absorption. For example, when oxochrome NH2 group is attached to benzene ring, it's increase in lambda max as well as E max as given below. NH2 acts as the oxochrome by extending the conjugation in benzene by the participation of non-bonding pair of electron in conjugation. Similarly, epoxy group act as oxochrome as shown below.